Let us see the operations on heap tree. Okay. So, general operations on heap are insertion and deletion. You have to construct a heap tree by inserting elements into that, and also you can delete the elements into the heap tree, right. What is heapifying? Okay. Suppose I have a tree with me with some max heap. I will take some 14 here, 7, 3, 2, 1, 6, 5. Oh, but it is not satisfying, no. Here I can put 13, right. 14, this is a max heap I have with me, 14, 7, 13, 2, 1, 6, 5. Okay. We talked about complete binary tree. So, if I want to insert a new element, I can insert it here. Suppose the element which I am inserting is 20. Okay. In this example, till here this tree was fine. Max heap property was satisfied. 14 is the root and that is the largest element. Then left and right child are lesser than 14. Again for 7, left and right are lesser than 7. For 13, left and right are lesser than 13. So, it is satisfying the property. Every element is lesser than the its root. Okay. But when I insert a new element 20 here, is the tree satisfying the heap property? No. As soon as I insert a new element into the tree, it is violating the rules of the heap property. Same like in AVL tree, when we were inserting, it was violating the height was not being balanced. So, we were doing some rotations. Same way here we will be doing heapifying. Okay. What is heapifying? After inserting an element or deleting an element, if the tree becomes unbalanced in the sense, if the tree violates the rules of heap property or does not satisfy the heap property, then you have to heapify the element, or you have to heapifying a tree, means bringing it back to a max heap logic. Okay. I inserted 20, because of 20 it is not satisfying the property of heap tree. So, heapifying is a process which will transform or convert this tree into a max heap tree. The process of adjusting this tree, which is not a heap, okay, trying to convert this tree into a heap tree is called heapifying. Okay. We have to adjust, we have to make some rotation, some movements we have to make, right, some swappings we have to do, somehow bring this 20 here, because that is the largest element, and the property of max heap is that always the largest element should be at the root. So, this 20 which I am inserting here, somehow I should do some transformations and bring it back to the root. This process is called heapifying. Okay, right. So, what we do here, see, in max heap, to heapify an element, we have to find the maximum of its children and swap it with the current element. Okay. Find out the maximum of its children and find its current element. Okay. So, here what is the property? See, I will just quickly give you what we are trying to do. I inserted 20 here. When I inserted 20 here, this is violating the property of max heap. So, what is the logic here? Its parent, okay, you find out its left and right child. There is no left and right child for 20. Go up, 2 is there. Find out the maximum of its left child and right child. Make that as the root. So, because of this 20 comes here and 10 comes here, 2 comes here. Then for next go up 7. Find out the maximum in its left and right. 20 is maximum, swap it with the root element. So, this becomes 20, this becomes 20 and this becomes 7. Then we have 20 here, find for its parent, that is 14, find out the largest of 20 and 13, 20 is the largest, swap it with the root. So, this becomes 20 and this becomes 14. This is how we can do the heapifying process. Okay. We are trying to do heapifying process by swapping it with roots and somehow bringing the element to the top of the in its correct position, making sure that it is satisfying the property of max heap. Okay. So, heapifying is nothing but if a tree structure, okay, if a tree is because of an insertion of a new element or deletion of a new element if the tree structure is disturbed. Okay, if the tree is not satisfying the property of heap, then you have to apply heapifying process. We have to apply heapifying process, where what we do in heapifying process, we try to swap the elements, compare and swap the elements and make it a max heap property. If we should make one observation here, if you see, when I inserted 20 here, right, I am doing operation from bottom to top, from bottom to top I am doing the heapifying process, first this root, then this root, then this root, and I can observe that this is nicely satisfying the property of max heap. Sometimes you may need to do it downwards also. When we have to do heapifying process, in heapifying there are two ways, one is bottom to top, the other one is top to bottom. Okay. When we have to use this, when you are inserting a new element, most probably you have to use this bottom to top. When you are deleting an element, you have to use top to bottom. Let us take same example, I have 14, I have some 7, 13, here I have 1, 2, 7, oh 7 is already there, 8 and 9. Okay. Suppose I am deleting an element, I am deleting the root. Okay, for example, I am deleting this root itself, I am deleting, or let us not, let us take a simple case, let us say I am deleting 7, I am trying to delete 7. When I am trying to delete 7, I want to delete this node, okay, this 7 I want to delete. Then what you have to do, find out the maximum element in both its children, and swap it, So, need not swap it, just put that here and you delete that particular thing. So, we deleted now, this is satisfying the property of heap. Okay. So, you have to keep doing this from top to bottom. In this case, it is a simple example. So, in one step it has gone, but if it is a very large tree, something like this, then it takes multiple operations for us to do. Then we go from top to bottom. Overall, heapifying is nothing but because of insertion or deletion, if the tree structure or the heap property is disturbed, then you have to do heapifying process. In that heapifying process, sometimes you may have to adjust the tree from bottom to top, sometimes you might have to adjust the tree from top to bottom. Okay. Let us see what are those. Right. In the heapifying process, since we are moving from top to bottom, this process is called as percolate down. Very, very important. If you are moving from top to the bottom, this is called percolate down. And if we start heapifying from any other node to the root, that is from bottom to towards the root, that is called percolate up. Okay. Percolate down, percolate up are two very important operations which help us in heapifying process. Okay. If I before I again go into deeper of these concepts, see, logic is simple. You are given some tree, a tree is given to me, I want to convert this to max heap, So, you have to apply heapifying property, What I am doing, when I am doing heapifying for this, I will start from the bottom node. Okay. You can do it from bottom or you can do it from top also, still you can convert that to max heap. How? For this 4 I have nothing, for 2 it is left child and right child, compare both, which is the maximum, 4 is maximum, swap it. So, 4 comes here and 2 comes here, same thing you do for left hand side. So, 5 comes here and here 3, then again compare these two, find out the maximum element and swap it. So, 5 comes here and 1 comes here, right. But again this is not satisfying, this 1 is not satisfying, again you swap it, you bring 3 here and 1 here. Like this, we have some algorithm which will help us in doing. But if you are moving from bottom to the top, it is called as percolate up, percolation process, adjusting process. Percolation means adjusting process. If you are doing from the last node to the top, if you are moving, that is percolate up. If you are coming down, it is called percolate down, right. So, percolate up and percolate down. What is the logic here in percolate up? Let us take one same simple example here to understand this. 20, I inserted it like this. Okay, this is my tree, right. So, index, this index, anyhow we are talking this in array, right? We are storing this in array, right? How are we storing? 14, 7, 13, 20, and I have some elements index 0, 1, 2, 3. So the newly inserted element is 20. Where did I insert? I inserted the element at index 3. That index I am giving as input 3. Is 3 greater than 0? Yes. Find its parent. How to find out parent? 3 minus 1 by 2. 2 by 2, 1. So its parent is at 1. So I got the parent as 1. If heap of index, that is heap is the name of the array, okay. Heap of 3, that is 20, greater than heap of parent, that is heap of 7. Yes, it is satisfying, no? 20 and 7, 20 is greater than 7. Yes. Then do swapping simply into t equal to h of I equal h of p equal temp. I have swapped it. So 20 comes here and 7 comes here, right. Then index equal to parent. Now my index I am making it as parent. What is my parent? Index 1. That's it. This is enough, no? So because of this, the structure changed 20 and here it became 7. But is it okay now? No, still it is not satisfied. Why? This is while loop. This is while loop. Index I became 1. From here again it will go back to the while condition. While index greater than 0, yes, I is greater than 0, right. Parent equal to 1 minus 1 by 2, that is 0. So parent is at 0, okay. So in this tree, if you see, now my index is at 1, parent is at 0. If h of index, that is h of 1, 20, greater than h of parent, yes, parent is 0, h of 14, it is greater than, then swap it. So make this as your 20 and make this as your 14 and update your index as parent, index becomes now 0. Again go up, while index greater than 0, 0 greater than 0, false, it will come to else and break, that is it. See, the tree is now heapified. So whenever you are inserting an element, sometimes you may have to use percolate up, sometimes you might have to use percolate down, okay. Logic is very simple, simply keep comparing with its root, whenever it is greater than, swap it. Let us see percolate down, okay. Suppose same example I will take 14, 7, 13, let us take something else here, okay, let us take 2. This is my tree, okay. So percolate down we will be using while we are deleting the elements. Suppose I am deleting, I will write the array structure here. So I will have 14, 7, 13 and 2, index 0, 1, 2, 3. Suppose I am giving index as 0, right. Size is the number of elements into this, that is 4. Size is equal to 4 because I have 4 elements. We will maintain a counter to hold the number of elements, that you do not worry. When we implement insert operation, we can understand it. So 2 into index plus 1, that is 2 into 0 plus 1, 1 is less than size, yes. Then left child is at 2, 1, left child is at 1, right child is at 13, that is left child I got it as 1 index, right child is at index 2. Why? Index is 0, no? This is what I want to delete. I want to delete 14, okay. Largest equal to index, so largest equal to index 0. If left child, that is 1, less than size, 1 is less than 4, yes, and heap of left child, heap of 1 is greater than heap of largest 14. Is this 7 greater than 14? Then largest equal to left child. This is not satisfying, 7 is not greater than this. Then if right child is less than size, yes, 2 is less than size, satisfied. Right child greater than largest heap. Is the right child 2, that 13, is it greater than this 14? No. Then third one, if largest is not equal to index, largest is equal to index, it is matching, right. So you need not do anything here in this percolate down. Why we need not do anything here? This is already in sorted order, right. So we are not deleting, but we are doing this process from top to bottom. Both are achieving the same thing, percolate up, percolate down, both will make sure that we are trying to build a max heap, okay. So, these are two important operations, percolate up and percolate down. If you are following top to bottom, percolate down, from bottom to top it is percolate up. These both functions help us in heapifying process. Okay. This is about heapifying an element in a heap tree.